Yesterday, we were talking about dropping objects on the moon, right? We were fighting about whether or not if we dropped 2 objects on the moon, they would fall at the same rate, fall at different rates, or not fall at all, right? Do you remember that? We were kind of like, are they just going to sit there? And we were talking about the astronauts, and we were saying, whether or not the astronauts are stuck down to the moon because they have like lead weights in their boots, or because their packs are so heavy, or because they've got some sort of other like mechanical device holding them there, like what's going on. So I really want to make sure this all makes sense. And in order to do that, I want to talk about gravity. We wrote a little bit of this down before, but we're going to write it down again because I think it's good. Okay, so gravity. Sure, yeah, or you can start a new page if you feel like you need to start fresh like I do. I'm like, let's just start new, okay? Do you remember we talked, I don't know, a couple of months ago when we first started talking about forces? We made a list of different, we defined a force as a push or a pull, right? Do you remember that? And then we made, this is a long time ago, like forever ago now in our kind of time frame. And then we had contact forces and we had non-contact forces. Do you remember that? And we made a list of non-contact forces. Does this sound at all familiar to you? Yes. Yes? It's like, I've got it right here. I have it in red and purple or whatever. Yeah, right? Like we did talk about it. And one of the non-contact forces that we talked about was gravity, right? So one of the things that, and this is just like fundamental stuff that I really want you to understand. Gravity is a funny force. Did I tell you what Albert Einstein called it? Spooky action at a distance, right? Like literally, yes. Quote from Albert Einstein. Not just gravity, but all of the fundamental forces are spooky action at a distance. It doesn't make sense why these two things are going to smash into each other. Why does it happen? There's nothing pulling or pushing, okay? Particle physicists right now are trying to actually show that there is something, but right now we still don't really know. What we do know is that any 2 objects that have what? Will be attracted toward one another. Maybe if I hide that there. Okay. Any 2 objects that have mass will be attracted toward one another. I'm just going to make sure this is still going. It is still going. That's awesome. Okay, now I won't bump it with my hand. Sweet. Okay. The amount, this is the part we haven't talked about yet. And we're not going to get into the nitty-gritty of this right now. We'll get into it later, but I feel like I need to tell it to you. The amount that they're attracted to each other, what do you think it might depend on? It depends on the mass, yep. So the amount of force mass of object 1 and the mass of object 2. Anything else that you think might come into play there?
Where these 2 objects are.
Absolutely. Where they are relative to one another, the distance between them. Yeah, yeah.
I thought you meant like between space and side.
So tell me more what you meant. Sorry, maybe I misunderstood you.
Like 2 different like areas, like if you're on Earth or if you're on space, the amount of force between them might differ. The attractive forces.
Okay, I think I understand. So let me ask you a question. Is there a gravitational attraction between me and the Kleenex box? According to what you said yesterday. Well, according to the same, I repeated it again. Well, maybe I haven't forgotten, right? 2, I have mass. Kleenex box has mass. So there is a gravitational force between us, right? Why doesn't the Kleenex box just fly towards me?
Because the Earth is a lot stronger.
The Earth has a whole lot more what?
Mass.
Whole lot more mass. I'm very, very small compared to the Earth, right? Are you with me there? Yeah, like orders and orders and orders of magnitude smaller, right? So the mass of the Earth is just ridiculously large. So the force that the Earth pulls on the Kleenex box is way bigger than me. Is that okay?
Yeah.
So that means that the Kleenex box isn't going to fly towards me. But if I rode on my spaceship and I took my Kleenex box with me, okay, and then I went far, far away from any planets or any stars or anything, and I placed my Kleenex box over here, and then I stood here, and I don't know exactly how I would do that logistically, right? Because it would be hard. But so something magically placed my Kleenex box here, and I was here. What's going to happen to us? We are going to come towards each other. Okay? Because there's no Earth to pull on me. There's no other stars to pull on me or anything like that. Does that make sense? Yeah. Okay. How are we doing? Are we okay? Ish. So far, like I haven't broken anything in your head, right? Is that true? Okay, good. So mass 1, mass 2, and the distance between. Sweet. Okay. So if I am standing on Earth, so here's the Earth, and here is me. Is the Earth pulling on me? Yeah, good call. I'm pulling on it too. But the Earth is definitely pulling on me. I've got mass. It's got mass. We're some distance apart. We can calculate it if we know the formula, right? Now let's say that instead I am on an airplane. Not drawn to scale, my friends. But let's pretend that I'm on an airplane. So there's my airplane, and here I am. Is the Earth pulling on me now? Is it pulling on me?
Yeah.
Sure it is. Yeah. How does the strength of its force compare when I'm in the airplane to when I'm on the Earth?
Less.
Probably a little less. We didn't actually define that, right? But as the distance gets bigger, the force is going to get smaller. Okay. Let's say that I go out on my rocket ship. Right? And here I am. As I'm flying away in my rocket ship, is the Earth pulling on me?
Yeah.
Yeah, it is. How does the force compare to when I'm on the Earth? It's less, but it's still there, right? Okay, let's go to the moon. Here's the moon. Here I am on the moon. Does the moon pull on me? Does the Earth pull on me when I'm on the moon? Well, does the Earth have mass? Do I have mass? Am I some distance away from the Earth? So yeah, the Earth pulls on me. Does the moon pull on me? Yeah. But the moon's going to pull on me a whole lot more because I'm much closer to it. Are you with me there? Okay, much, much closer, so it's going to pull on me more. You with me there? I take my objects to the moon. They're going to fall just like they would anywhere else. But the acceleration here on the surface of the Earth is at 9.81 that we keep talking about over and over and over and over. The acceleration on the moon is not going to be 9.81. Okay. Hey, Gerald, it's nice to see you. Nice.
This is a pass. I have to go.
You're leaving me? Okay.
Yeah.
Catch you later. We'll miss you. We're recording this, so you can watch it and then you can listen to me say, "Hi, Gerald," and it'll work out really well. Sound good? Okay. Whatever. So on the moon, will stuff fall?
Yes.
Yes, absolutely it will. Okay. That's the first thing that I want to get in your head. I want to show you a quick video.
Because,
Oh, go ahead. Keep talking.
wait, maybe it's dumb.
No, not dumb question. Keep talking.
It'll fall because it has gravity or because there's mass pulling from the Earth?
What was I dropping yesterday? I don't remember.
Flower petals, squash, and a pencil.
Oh yeah, the squash and the pencil and the flower petal and all those things. Yeah. So, excuse me. Why will my butternut squash? There's my butternut squash. Why is it going to fall towards the moon? What does it have? And what does the moon have? Mass. Quite a bit of mass. And there's some little distance between them. Okay? So it will fall. Does that make sense, Maddie?
It'll fall because it has mass.
Because it has mass and the moon has mass, and so they're going to be attracted.
Does that have anything to do with gravity?
Yeah.
Okay.
Gravity is the force
Okay.
that makes them fall because they have mass.
Okay.
Does that better? Okay, awesome. Okay, now we had our flower petal and we had our pencil. We dropped them on the earth. And what did we decide was going to happen on the earth when we dropped them? What was it? I don't remember, you guys. A flower petal and a what?
And a pencil.
And a pencil. Okay. I'm just trying to find papers that I don't need anymore here. I don't want to throw away somebody's work. All right. Got two pieces of paper. Which one has more mass? We'll assume that the ink is approximately the same amount. They were both printed on both front and back.
They'll be the same, but
Same mass, yes?
it depends on the surface area.
Okay, so when I drop them on Earth, which one's going to hit the ground first?
Because it's
Purple or white?
purple.
Purple.
Because that one will have more air resistance and it'll float.
Right. You okay with that?
It's like those leaves that you throw up and they come.
Yes, yes, yes. So now I'm going to get on my rocket ship. I'm going to fly to the moon. I'm going to do the same thing. With my purple paper and my white paper, what's going to happen? Can I go to the moon wearing this, walk out on the moon and say, "Hi, Haley, how's it going?" Will that work? No. Why not? I would die. Why would I die?
No atmosphere.
There's no
Atmosphere.
atmosphere, also known as 3 letters, starts with an A. Spelling! I mean, I don't spell well either, right? Air, right?
Okay.
And when I drop these, Maddie just said that the reason that the white one falls slower is because of what? Air resistance. So if I go to the moon just wearing this and I don't wear my fancy pants spacesuit, okay, I will die. The reason for that, do you guys know why? My lungs will collapse because there's no pressure to keep them open, right? They're just like little balloons. Okay? What's that?
Who figured that out?
Well, I mean, they didn't like take somebody to the moon and try it, but
There's a ton of different ways to tell pressure.
yeah,
I bet
you can,
did.
we'll get there.
I would say that's
Just not today.
interesting.
I
So-
bet you they did test that. They were probably like, what happens when you take your spacesuit off?
Woo!
I just don't hear about
Right?
that.
Yeah. Right.
Because it's-
And here's a question. Oh, this is another interesting question. This is something totally unrelated, but it's interesting. Let's say somehow I made some sort of like bionic thing so that I could take my helmet off. And I was feeling really generous. I took Haley with me and I gave you the same fancy space suit, right? That like so I could take my helmet off and like look around. And I'm like, "Hi, Haley. Can she hear me?" There's no what?
Sound waves.
Well, you're right, but why? That's what I want to know. We're learning new physics.
Whoa, you can't hear things in space?
You can't hear stuff in space. Why not? Liam just said it. Say it loud and with authority.
Because there is no like medium for the sound to travel through.
Is there large or small? What do you mean there's no medium? What does medium mean?
Like there's no mass.
Sound
Yeah.
carries through vibration.
Yeah, sound goes through stuff like that 3-letter word that starts with A. Air. Let's try that again. What is it?
Air.
Air. I just pointed a little too high there. There's no air. The reason you can hear me is because my vocal cords vibrate the air, which is the medium that the sound waves travel through, right? And then those sound waves hit your eardrum, and that's how you hear me. Okay? On the moon, or in somewhere of interstellar space, there is no
Air.
high five for that. All right. There's no air, so we can't hear each other, and we can't breathe, so that's really sad. But is there gravity, friends?
Yes.
Absolutely. If there wasn't, we would not be here. The Earth would not go around the sun. The moon would not go around the Earth, right? None of that would happen if there were no gravity. It'd be a sad day. Okay. Yeah, but we would like there would not be any you
There'd be no grade.
because your cell, right? Like no, none of
It
it.
would dissipate.
Wait, without us, there's no grade.
I'm going to show you a couple things here.
I'm kind of thinking.
Abdul, can you turn the front set of lights off for me?
Yeah.
So this is the video I've promised you for ever. No, hold on. I'm gonna. How's it going there? All right, hold on. Let me put this
That
on.
next one. I've seen that video.
All right. So this is the one that I mentioned to you before. This is David Scott. He was on a lunar mission, right? So he's going to come out of the lunar lander right here. That's the American flag on there, but you can kind of see where that is. He's going to come down and he'll explain what he's going to do. What's that? No, I think he's going to, I don't remember. We'll just find out. Let's just watch. Oh, I can't hear. Turn up the volume. There we go. All right.
Sinusometer drum in the ETB.
Not quite yet. I haven't put the link in
There he
yet,
is.
but I will shortly. I want to watch this. Joe, you have a good picture there. I've got the...
Beautiful picture, Dave.
Grandpa, in my left hand, I have a feather. In my right hand, a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago. He had a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. About that. I proof that Mr. Galileo was correct in his findings.
Did you guys see that? Did you catch what happened?
They drop at the same time. He didn't fly to the moon just to do that, right?
No. They were doing plenty of other things. But this was one of those quintessential, like, we have this opportunity. We can do this. We can prove this. We don't have to go to the moon to do this, right? If you get a container and you evacuate all the air, also known as starts with a V, vacuum, good work.
Oh.
Not like the kind that you clean with, but a vacuum means when you take the air out, right? So if you have a vacuum tube, okay, there are other videos, yes, but yeah. So you can do this. So you can take a feather and you can take a hammer, you can take a rock and you can take a whatever. I don't have a vacuum thing yet, but someday maybe I can get it done before then. We'll see. When you drop them, they will fall at the same rate. Can you guess what the rate would be if we do it on Earth? 9.81, right? When you did the lab with Mrs. Ellickson forever and ever ago, when you dropped things and you measured the acceleration due to gravity, you should get something close to 9.81. Part of the reason that I like to do that lab too is because I also get out the puppies and we drop the puppies. When the little fuzzy puppies like I had up here, before the little stuffed puppies, not real puppies, come on, Janelle. No, the fuzzy puppies. And as we drop them, tell me what you think. The acceleration that you measure for the puppy compared to the ball's going to fall at close to 9.81, not exactly, but close. But tell me about the puppy. Is the puppy's rate going to be greater or smaller? Or the
Depends how
same?
big the puppy is.
You're talking about the
I like the
acceleration,
frog.
right?
I'm talking about the acceleration. So if I take, my frog has a lot of mass, so it's not quite the same. But if I drop my frog and I drop this ball, which one would hit the floor first? Yeah, because Frog's heavy. Darn. Okay, my puppies are really light. They're kind of like this. Which one's gonna hit the ground first? This one, right? The purple one, the ball, right? Because there's air that's pushing back up this way. Are you with me there? Okay, we're gonna get there in just a second. But I also want to show you one other thing first. Because no one has asked me again today about this whole floating business. Some of you yesterday, when we were fighting about whether or not gravity existed on the moon, you were convinced that gravity didn't exist in space.
No.
Some of you said that. I
That
don't
was
remember who.
probably me.
It was Jill's like, maybe it was me. How many of you have seen some sort of movie, real or not,
Where people float.
where people what?
Oh.
Float!
I know.
Right? Have you seen this?
I always
Yes.
wanted to do it.
You've seen Apollo 13. Maybe you've seen Interstellar. Maybe you've seen The Martian. Maybe, whatever it is. Pick one of them. I don't know. I've not seen Tron, but yes. Yes, for sure. Wherever,
Not a space movie at all.
anytime there's floating, it looks like there's no gravity, right?
That is
Yeah? It looks like there's no gravity. So here's the thing. There is gravity. What does it mean to be floating? That's what I want to know.
Well, in the
What does
pool,
it-
I think it's when you're on your back.
That's true.
What does it mean to be floating like in space? What does that mean?
Wait.
That's like a big like philosophical
You
question,
have
right?
no mass.
Which
What?
one?
Wait,
You-
no.
So here's the thing. I have to tell you something.
No
You
weight.
were very, very close,
No weight.
and everybody ridiculed you, but you were close. Do you have mass?
Yes.
Yes.
Yes, mass means the stuff in you, right? You have cells, you have, right? Like there's mass. But what does not exist?
Wait.
Weight.
Oh
So
wait,
you're
sorry,
telling
I
me
get
if I
confused
step
between
on
both of
the
them.
scale-
Now here's
I'm
here. Hold on just a second.
So
Hold on just a second, because I want to make sure I'm answering all these questions. So we're gonna go this way, and then we're gonna come this way. I'm not ignoring you. Go. What were you
No,
gonna say?
I get confused between both of those. I'm sorry. I meant one of them.
It's okay. It led to a lovely conversation, so I'm okay with it. Go.
So if you step on a scale on the moon, you're gonna weigh nothing.
No.
It'll be zero.
No, I did not say that.
Like, just
Are you? If I go to the moon, am I going to be floating?
you step on a scale in space.
So that is it right there. Like, boom! If we were just going to like bottle one comment, that's the comment right there. So embrace it, enjoy it. What did you just say?
In space, I step on a scale.
If you step on a scale in space. Okay, so if I step on a scale right here, I step on that scale, it's going to measure my weight. How does it do that? How does it do that? Let's talk. I think we're there almost, but let's get there. So here is my scale, and here am I. And what is the scale doing?
Weighing you.
Weighing me, yes. Like, oh, hello, I'm going to weigh you now. What does it do? Does it apply a force to me?
Yes.
Yeah, it's
Yeah.
what's holding you up.
Mm-hmm. Yep, so the earth is going to pull me down, the force of the earth, right? On me. And then I've got the force of the scale on me, right? And if I stand on that scale, the scale's going to push up within the amount of force that is necessary to keep me from accelerating. Okay? Any of you, I think most of you have more mass than I do, and I don't mean that. I'm not at all trying to comment on your size, just that I am particularly a small person, okay? So if you stand on that scale, how is the force of the scale going to compare to the force that it pushed up on me with? It's going to be pushed more, right? Because you have more mass, so it's going to push up more on you because the force of the earth on you is bigger. Are you with me there? Okay. So now, let's imagine taking that scale to the moon. Now, instead of it saying Earth, it's going to say moon.
But then, would the scale even like be on the moon? Like,
I have to pack it in my bag and then bring it down like
Oh, it'll stay
David
on?
Scott. Yeah,
The moon has gravity.
yeah, the moon has gravity, right? We just saw it. He dropped the feather, did it? It fell.
I'm just making
So how does the rate of falling on the moon compared to the rate of falling on the Earth? It's smaller. You know this equation that we wrote over here, the force of the Earth on the object? If I was going to write the same thing, the force of the moon on the object, it would be the mass of the object, just like we had before, times some other number.
Smaller?
Some smaller number. It's something, I can't remember. I'm going to say it's something on the order of like 4.5, but I can't remember for sure, so don't quote me on that. I'll look it up in a little bit to tell you for sure. But it's something like that. Are you with me there?
You're telling me that when I do my height and weight in PE, I'm going to say, I'm going to cut my weight in half and tell him I weigh that, and then he'll look at me funny and I'll be like, well, on the moon, that's how much I weigh, so
Yes.
I'm going to do it.
That's exactly right. So if you really like have some sort of thing where you just really want to have a certain weight, you just find the right planet or celestial body to stand on, right? Not stars, because it would be hot, but you know what I'm saying? You can find whatever planet you want or whatever moon you want, and you can weigh whatever you want. Are you with me there? With the same amount of mass you have. No? That would be unhealthy. And I really want to be clear that I'm not trying to body shame or anything like that, because you are all beautiful people. Making that really clear. Yes? Yes, yes. Okay? But your weight on the moon will be smaller than your weight on Earth. Okay? Because the acceleration is smaller. Now, so Maddie goes to the moon, she weighs herself, she's like, sweet, I got such and such a weight. And now on your ride back. You with me there? Okay? You're floating. We're not sure why yet, but you're floating. Your scale is doing what? Floating. So if you're floating and your scale is floating, is it going to apply any force to you? No, so it's zero. So you have no weight. That's what weightless means. Okay? That's something that I want you to write down right now. Here it comes. Weightless does not, I'm going to highlight that. I'm going to put some sparkly colors on there. Okay? Does not mean no gravity or mean okay? Weightlessness does not mean that gravity does not exist. Excuse me. It simply means that anything that you're going to use to measure your weight is not able to push up on you, okay? It really means there's no normal force. Okay? I'm going to show you a quick video. This one I just found today, but I really liked it. My husband, oh, sorry, go ahead. Yeah.
It's 30.
Oh my gosh. Okay. Sweet. Jeepers creepers. So, my husband really, really likes airplanes. Like that's something that he just has a fascination with is airplanes. And we go down to Arizona most spring breaks to watch baseball. And there's also, if you're ever in Phoenix, there's a really, really great airplane like museum. And there's like hundreds of airplanes just out in the desert, like in Phoenix, like outside of Phoenix. It's awesome. The Pima Air and Space Museum or something like that. We've been there many times. But anyway, there's this one airplane that's my favorite airplane to see every time. What's that? No, it's not. It's a airplane that's called the Vomit Comet. The Vomit Comet, which I just like the name too, but I like the Vomit Comet because of the physics stuff that's involved with it. So I'm going to show you the video first, and then we'll talk. I might pause the video a couple times too. But, what? Partially because he's colorblind, and you can't be a pilot if you're colorblind. Partially. But also just because he's also fascinated with other stuff. Yeah. So, yep. All right.
Hi, I'm Kelly Downs from RIT's University News, and I'm here at NASA in Houston, Texas, where a team from RIT earned a coveted spot to fly aboard the DC-9, NASA's weightless wonder. This research aircraft is the ultimate roller coaster ride, peaking at 34,000 feet over the Gulf of Mexico. The plane follows a parabolic flight path to produce weightlessness. A typical flight consists of about 32 arcs. As the plane climbs towards the top of the parabola, passengers feel the force of nearly 2 Gs, or twice their body weight. Once the plane starts to go over the top of the invisible arc and begins descending back toward Earth, flyers free fall, experiencing nearly 25 seconds of zero gravity. The passengers, and any objects not nailed down, are weightless.
You're floating there in the middle of the aircraft and your mind's kind of going all over the place saying, this isn't right. And you're just trying to, I guess, get your bearings all the time.
The plane is more commonly known as the vomit comet because of its reputation to wreak havoc on the human stomach.
Another man down.
Each year, collegiate teams from all over the country submit proposals to NASA to be part of its Reduced Gravity Student Flight Opportunities Program. The space agency selects the top proposals. Greg Sharp, Christopher Ubelacker, Jarrett Whetstone, and James Craven represent RIT.
It blew my mind when I first heard that we were gonna be accepted into the project. So I'm like, it's a lot of work, but it's completely worth it.
In July of 2008, RIT's team heads to Johnson Space Center for a week, which culminates in a climactic 90-minute flight to test an experiment in zero gravity. The RIT team's experiment looks at the feasibility of inkjet printing in a weightless environment.
We were testing the ability for inkjet printers, both piezoelectric and thermal print heads, to function in microgravity.
RIT is in great company with other big-name schools invited to participate, including Texas A&M, University of Kansas, University of Arizona, University of Florida, and University of Texas. Design engineers review the projects to ensure they are safe to fly.
This is our test rig, and basically inside we've got our printers, everything's encased within this outer structure.
The health and safety of the students during flight is also of the utmost importance. As part of the pre-flight preps, the students go into a high-altitude flight chamber to experience the symptoms of oxygen deprivation, what's known as hypoxia.
Looking for some outward signs of hypoxia. You may start to notice a little bit of belligerence in someone where they're normally cool, calm, and collected, and all of a sudden they want to start a fight.
Finally, it's flight day. RIT's team goes up 2 at a time. First up are Chris and James.
He's ready to go.
We were testing thermal and piezoelectric methods of inkjet printing in microgravity, which consisted of 2 different tests. Printing out standard targets on standard letter paper, see if there was any changes in the quality of the print, and we also use a high-speed camera to actually image a droplet from both technologies to see if there's a difference in size, shape, speed, and amount of actual inkjet droplets.
Next to fly, Greg and Jared.
And we're testing printers in zero gravity. And floating all over the place.
To begin with, we started setting up the high-speed camera and the printers, so that as soon as we got comfortable with the parabola, which was button number 3, we were able to immediately just get into capturing high-speed video.
For long-term space missions, the students believe the printhead technology could potentially be used for other applications besides just printing out sheets of paper.
Hopefully the printer will be able to make circuit boards or something similar, because the technology just places small volumes of liquid into a very accurate location. So any real application that you would need to do that could potentially use this data.
The experiment finds both inkjet printing technologies are capable of working in a weightless environment, but there is room for improvement. In zero gravity, there's no force to hold the moving printer parts in place, which degrades the printer's effectiveness. After the teams get their data collected, it's time for some fun.
I had a blast, so really excited that I got to go. A lot of fun. It was actually pretty fun. You start floating, and you wonder what's going on, and your feet have a tendency to easily go above your head.
So, Did the vomit comet live up to its nickname?
Sure did. Got a little queasy there, somewhat halfway, but still doesn't ruin the experience for me.
It did at the end. It was a very rough flight. Weightlessness is quite an interesting experience, as well as the nausea that comes with it. Luckily for me, I did not expel anything.
The NASA flight crew includes videographers and photographers who document the students and their experiments.
So just talking about some of their albums.
Markowitz was the still photographer on the Vomit Comet during the filming, an experience he says was one of the best of his career. Markowitz spent weeks with director Ron Howard and actors Tom Hanks, Kevin Bacon, and Bill Paxton as they flew the zero-gravity arcs to recreate the historic space mission. Of the 6-member photography team at Johnson Space Center, half are RIT alumni. All grad.
Okay, so were they floating? Yes. Were they experiencing gravity?
Yes.
Yes, absolutely they were. They were not up any higher. Have you guys all been on an airplane before? If you've ever been on an airplane before, they were experiencing the same, they were up at about the same height that we would be when you're flying, okay? It's not that they were far, far away and there was no gravity. Remember they said when they go up, they were being pushed up. Are you with me there? Okay, so they were actually feeling twice normal gravity. So don't get your scale out then, right? Get your scale out then, you're gonna be twice as heavy, right? You weigh twice as much. Are you with me? But when you fall, okay, if you've ever been on, is it, what's it called? The space shot at Adventureland? Or what's it called at Adventureland? The big tower.
Yeah, I know what you're talking about.
What's it? Is it space shot? Yeah. If you've ever been on that, when you first start to fall, for the first like half of the descent, you are weightless. That's when your butt comes up off the seat and you're like, whoa, and your stomach feels kind of crazy, right? Same kind of deal. This is just a longer amount of time than we can build a tower. Are you with me there? Okay. So how are we doing? Are we okay? Do we get this gravity business?
They had like a 98-year-old woman go there, and she wanted to be like the record, and she went again and again, like I think 130 something times in a row.
That's a lot of times in a row.
I mean,
Why?
14 times in a row this summer because the lady we made friends with, she was like, "Oh, you guys can just stay on."
Why?
I felt sick after like the 4th.
Yeah, right. I would say so. Absolutely. Okay. To write it 14 times in a row? Not after you've eaten a
Yeah, see, I ate, and I was like,
oh yeah, like a funnel cake or something like that. That sounds like that. Yeah. No. All right. How are you doing with this? Are we okay? Okay. We need to touch base about the rest of our plan for the rest of the week. Here, ladies and gentlemen, we're not going to do a lab because we don't have time to do a lab anymore. I am going to work on developing a test in the next little while. I haven't done that yet because I was working on a test for next period. A test for you guys?
like a test that we can.
I don't know. Let me work on it. Let me develop it first. What I really want you to work on, I will stamp this homework tomorrow, okay? I want you to work on your problem set. I want you to get as far as you can, okay? I will give you guaranteed promise, Ms. Carbling promises, and it's recording me, okay? I will give you some time tomorrow as well. We'll touch base. Does that sound fair?
Yeah.
And then we'll figure out, because we need to do a little bit of air resistance stuff just because it's interesting and important. But does that seem like a fair deal? Okay. And we'll do some sort of test. But you know what? We really aren't quite done, are we? No, we're not. We're gonna write down a couple things here before we are done, because we have another 5 minutes still, don't we? Because we're not done until the 47. We got lots of time.
These clocks are like
They've been ringing like 3 minutes like early.
Okay, well we'll start
And
talking.
look at them, like it looks like the clocks are late.
all day.
No,
Yeah,
they've
they're
been early.
They've been early. They've been like 3 minutes. Like that clock says 1:44.
Yeah, that's why I put my stuff
It's
away.
141 right
And it's 1:44.
Yeah. They've been really.
Like the lunch bell rang like 3 minutes early. Because I didn't, I got to class early and it rang before I even got to class. And I was like,
All right, let's talk about air resistance for as many minutes as they let us. Okay, we'll see. Tell me what you know about it.
And you place with an atmosphere.
Yeah, we have to have air, right? Yes, yes. So it affects objects when air or an atmosphere is present. Awesome. What else do you know about air resistance? What do you think might affect the amount of air resistance that you experience? The surface area? Like it's, tell me more what you mean. No, I think you're on the right track. So density is kind of funny. The only reason that I'm kind of hesitating about density is that density is funny because it has to do with both mass and volume, right? Yeah, and so I think maybe, I mean, I guess you could kind of go there. I'm gonna give a shout out to the mass. Is that okay? Mostly because the volume part of it fits in with surface area a little bit more, if that's okay. Anything else that we know about air resistance? Do you think that the amount of air resistance that something experiences is constant, or do you think it changes depending on stuff? It's kind of a vague question.
What did you think about wind?
Well, I'm kind of thinking about wind. Like, what about the example of if you roll your hand down, it's a nice day outside, right? Like the super first nice day of spring. You roll down your window in the car, right? And you stick your hand out. You're driving slowly, and do you feel a little bit of air resistance on your hand?
I like.
Yeah. Oh, she
I
goes,
do that all
right, but if you go,
You do that, or she'll stick her foot out the window.
safe rider right here. Yay. I'm hoping not while you're driving.
Yeah, she does.
I mean,
Stick your foot out. She's super flexible on her
I
left side,
normally
so
drive
she'll
like
just,
this.
put her foot there. Yeah, and she'll be like up here like here. I'm like, how do you do that? I'm
That's
like over here like, ugh.
all right.
I drive like that sometimes.
If you're not like Tatum, but you just stick your hand out the window, let's keep it simple for a second. Stick your hand out the window, you're driving 10 miles an hour. You feel a force, right? If you stick your hand out the window while you're driving 55 miles an hour, probably not as recommended. Tell me about the force. It's a lot more. Has the surface area of your hand changed?
No.
Has the mass of your hand changed? Has the atmosphere, the speed is going to affect it, right? Yeah. The speed at which you travel. Okay. The speed at which the object moves will also affect the air resistance. Most of the time when we draw free body diagrams, we just draw free body diagrams and we ignore air, right? I think I may have told you that at the beginning of the year, like ignore air resistance, except when I tell you not to. So this is the time. And we're not gonna do any calculations with it. We're just gonna think through a little bit here. Oh, tomorrow we will.
And see, it's
And it ran early, it's 1:45.
It is. I have to talk to somebody about that. Whatever. I hope you guys have a great day.